If the policy is the student in RLHF, the reward model is the judge, and the whole pipeline is only as good as that judge. In this notebook, we build a reward model end to end. We start from the Bradley-Terry model, write its loss in a handful of lines, train it on real human preference data, then hunt for the ways it quietly breaks. By the end, you will be able to whiteboard a reward model pipeline and explain exactly why each piece is there, which is precisely what an alignment interview probes. So what is a reward model really? It is a learned scoring function. You hand it a prompt and a response, and it gives back a single number where higher means better. That number is the signal the policy chases during reinforcement learning. Think of it as compressing messy, expensive human judgment into one fast, differentiable score that you can query millions of times. Get that score right and everything downstream has a chance. Get it wrong, and you are optimizing toward the wrong thing. The obvious idea is to just ask humans to rate a response on a scale of 1 to 5, and train the model to predict that number. It does not work well. Those absolute scores are noisy and miscalibrated. One rater's 4 is another rater's 3, and rating on a scale takes real cognitive effort. On top of that, doing a human rating inside every reinforcement learning step would be far too slow, because the policy needs thousands of reward queries per batch. We need something cheaper and more reliable. Here is the key human insight. People are much better at relative comparisons than absolute scoring. Asking is a better than B is easier and far more consistent than asking rate this from 1 to 7. So instead of collecting scores, we collect comparisons. That single switch from rating to ranking is what makes preference data reliable enough to train a model on, and it shapes everything about how the reward model is built. That means every training example is a triple: a prompt, a chosen response that a human preferred, and a rejected response they liked less. Concretely, the prompt might be explain quantum computing simply, with one clear answer marked chosen and a vaguer one marked rejected. The model never sees an absolute label like good or bad. All it ever learns from is which of two responses won. And the whole job of the reward model is to make the chosen response score higher than the rejected one. Now we need a model that turns scores into preferences. That is the Bradley-Terry model, and it is worth deriving slowly. Step 1. Assume every response has a hidden quality score, the reward. Step 2. The Bradley-Terry assumption. The probability that the winner beats the loser depends only on the difference of their scores, not their absolute values. That little assumption, that only the gap matters, is the entire foundation. And it is why a reward model is only ever pinned down up to an added constant. We turn that score difference into a probability with the sigmoid function. The probability that the winner is preferred equals sigmoid of the winner's reward minus the loser's reward. Picture it. If the winner scores way higher, the gap is large and positive. Sigmoid saturates near 1, and the model is very confident in the preference. If the two are tied, the gap is 0. Sigmoid gives 1/2, a coin flip. The sigmoid is just the smooth bridge from a real valued gap to a probability between 0 and 1. Step 3. Maximum likelihood. We want to maximize the probability of every observed preference, which means minimizing the negative log of those sigmoids, averaged over the dataset. And here is the punchline that interviewers love. This is literally binary cross-entropy. The logic is the reward difference, and the label is always 1, because the chosen response is always the positive class. So a reward model is, underneath, a logistic regression on the gap between two scores, and that reframing makes the whole thing feel a lot less mysterious. Why this model and not something fancier? A few reasons. It is the simplest model consistent with the axiom that preference depends on the reward gap, and it is the logistic cousin of the older Thurstone model, swapping Gaussian noise for logistic noise. And it is a proper scoring rule, which means the reward model that minimizes this loss actually recovers the true human preference distribution, not some distorted version of it. Simple, principled, and correct in the limit. That combination is exactly why it became the default. In code, this is almost anticlimactic. You take the chosen rewards, subtract the rejected rewards to get the gap, then take negative log sigmoid of that gap and average over the batch. That is the entire Bradley-Terry loss, about 2 lines. A quick reason for using log sigmoid directly rather than sigmoid then log. It is numerically stable and avoids overflow when the gap is large. If an interviewer asks you to write this from memory, this is the whole thing. Always sanity check a loss before you trust it. When the chosen reward is far above the rejected, the loss should be near 0. The model is right and confident. When chosen is far below rejected, the loss should blow up. The model is confidently wrong. And when the two scores are exactly equal, the loss should equal the natural log of 2, about 0.69, because the model is predicting a 50-50 coin flip. That log 2 value is your random baseline, and you will see it again on the training curves. If you plot the loss against the reward gap, you learn a lot. It is convex and monotonically decreasing, so a bigger correct gap always means lower loss, with no nasty local minima to get stuck in. The gradient is steepest right around a gap of 0, which is exactly where the model is uncertain. So the loss pushes hardest on the pairs the model finds confusing, and gently on the ones it already separates well. That is precisely the behavior you want from a training signal. Now the model itself. The recipe is a pre-trained language model backbone with a scalar reward head bolted on top. Tokens go into the transformer, you pull out a hidden representation, and a single linear layer projects that vector down to one number, the reward. Crucially, you throw away the language model's original head, the one that predicts the next token, because we do not care about generating text here, we only care about scoring it. The backbone supplies all the language understanding. The head just reads off a quality score. 2 design choices to be deliberate about. First, which hidden state feeds the reward head. For a causal model, you use the last real token because it has attended to the entire sequence, so its representation summarizes the whole response. You carefully pick the last non-padding token, not literally the final slot, since padding would give you garbage. Second, the head is just one linear layer mapping the hidden dimension to a single scalar, plus a little dropout. Keep the head simple, let the backbone do the heavy lifting. There are other ways to pool the sequence into one vector, and knowing the trade-off signals depth. The last token is simple and standard. It is what Instruct GPT used. A CLS token works for encoder-style models that were trained with one. Mean pooling averages every token, which gives more stable gradients but dilutes the signal with padding. Attention-weighted pooling is learned and expressive but adds complexity. In practice, last token plus a single linear layer is the dependable default. What backbone should the reward model use? One school, the Instruct GPT approach, makes the reward model the same architecture as the policy it will score. Another makes it a separate, often smaller model for efficiency. In this notebook, we use a small distill-BERT so it runs in a free notebook, but keep the scale gap in mind. Production reward models are routinely many billions of parameters, sometimes as large as the policy itself. The principle is identical, only the size changes. For training, we use Anthropic's HHRLHF dataset, real human preference data collected to make assistance helpful and harmless. Each row already carries a full conversation in 2 versions, a chosen branch and a rejected branch. We shuffle, take a couple thousand examples for training and a few hundred for evaluation, just enough to learn the mechanics without a giant compute bill. The point is not a state-of-the-art model. It is to watch a real reward model actually learn from real human choices. The dataset wrapper tokenizes both branches of every pair, the chosen conversation and the rejected one, padded and truncated to a fixed length. So each training item carries 2 token sequences. During training, we run both through the same reward model, once for chosen and once for rejected, to get 2 scores. Notice the 2 scores come from one shared set of weights, which is what lets the model learn a single consistent notion of quality rather than 2 separate ones. The training loop is the Bradley-Terry idea made concrete. For each batch, score the chosen responses, score the rejected responses, feed both into the Bradley-Terry loss, then backprop and step the optimizer. We use Atom W with weight decay and a small learning rate, on the order of 10 to the -5, because we are gently nudging a pre-trained backbone, not training from scratch. And we clip the gradient norm to 1, a cheap insurance policy against the occasional exploding gradient that would otherwise wreck a run. Loss alone is hard to read, so we also track pairwise accuracy, the fraction of pairs where the chosen response outscores the rejected one. That maps directly onto the human question: did the model agree with the people?